Hi, everyone. Today, we're going to be looking a little bit more closely at convection. Convection is the second way that we're going to talk about that heat moves. Should you need to get a hold of me, my email address is on the screen. It's rcrawford@jcpsmail.org. So, to begin with, before we get to convection, we need to make sure that we're all on the same page with two different ideas. Um, so one of those ideas is density, and the other is thermal expansion and contraction. So let's take a look. Here's the statement that we're starting with. Heating or cooling an object causes changes in its density. Okay, so let's take a look. Let's start here with density. So first off, density is a property that all matter has that describes how crowded together the particles are. Okay, let's take a look at this example. Here I have a cube that measures 2 centimeters by 2 centimeters by 2 centimeters. And inside this cube, I see that there are 15 atoms. Now, if I were to make some general descriptions of this cube, I would say that this cube has very few particles in it. I notice that there's lots of empty space in here. These particles aren't very crowded together. As a result, I would refer to this cube as low density, or I would say that it is probably less dense. Okay, now let's compare this cube to the cube right next to it. Notice that it measures 2 centimeters by 2 centimeters by 2 centimeters, but it has 3 times as many atoms. It has 45 atoms in it. Now, this cube has, well, first off, has many more particles in it, right? 3 times more particles. And because there's more particles, that means that there is less empty space. Very clearly, this cube is way more crowded than the cube we looked at to start with. So it would be accurate to describe this cube as high density or more dense. Okay? So density is really just a property that describes how crowded together the particles in an object are. Less dense objects tend to be lighter, more dense objects tend to be heavier, if you would like to think about it that way. Now, one property that is connected to density is whether or not something floats or sinks. So in general, less dense objects tend to rise or float in fluids. So if we were to put this cube in water and it was less dense than the water, it's going to tend to float. Whereas if we were to drop this cube in the water, it's not going to do that. If it's more dense than the water, it's going to tend to fall or sink. Okay. Here's the big idea. Remember, we started with heating or cooling an object changes its density. So heating and cooling an object changes its density. So when we talked about thermal expansion and contraction, this idea that when we cool an object, it gets slightly smaller, and we said that's because that the particles actually get a little closer together, right? There's fewer collisions, so the particles can move closer together. Whereas on the other hand, thermal expansion is when we heat an object and the particles actually collide more violently and push each other further apart. So when this is exactly the definition of a change in density. Uh, when we have thermal contraction, this is actually going to make the object or the substance slightly less dense, which can make them rise or float. The opposite also is true. If we have thermal expansion, whenever these particles spread out, right, that gives more empty space in there, that's going to make them slightly more dense, which can make them fall or sink. To understand what's going on with convection, you absolutely need to keep in mind that density is how crowded together the particles in an object are, and that less dense objects tend to rise, whereas more dense objects tend to sink. And then we need to remember that changes in temperature can bring about these changes in density. So let's take a look strictly at convection. First off, I want you to notice that convection, we've said, is heat convection is heat flow in the circular currents of fluid. Remember, convection only happens in fluids, and by that I mean liquids and gases. So here we can see in this diagram, we have a heat source, right? The gases are up above this heat source. And now here, this is a zoom in. We've magnified to be able to look at the particles that are part of these gases, okay? So here's our heat source, and here are the particles. So let's see what's happening here. I really want you to follow along on this left side. So when we heat part of a fluid, right? So this fluid, the gas that's directly above the heat source, when it's heated, That's going to make those particles closest to the heat source, they're going to move faster and further apart. They're going to expand. Of course, this is going to make this particular part right here of the fluid, it's going to make it less dense. And remember, we said that less dense things tend to float. And maybe you have heard that hot air rises before, or maybe you just know that you shouldn't put your hand directly above a flame like a candle or a match or a campfire. This is why. Um, because we have these hot gases, this hot part of the gas that is beginning to rise up here and move that heat with it. So it's gonna begin floating up, or it's gonna begin rising because it is less dense. So as that hotter fluid rises up, as it's moving up, it's going to come in contact with other parts of the air, and it's going to start giving some of its energy away. So you can see that here in our animation, whenever these particles of air, they're colliding with, some with these other particles of air around them, they're giving some of that heat energy to them. When they give that heat energy to these other particles that are already cooler, they transfer some of the energy. And so when the energy of transfer begins, that means that that hotter fluid is going to begin to cool down. So if we have a fluid cooling down, that means that those particles in that fluid are going to begin to contract, right? They're going to be able to move closer together. And remember, that's going to make it more dense. More dense things tend to sink. So these cooling particles, now that they're moving slower and closer together, they're going to begin to sink again. And this is what's going to create convection. Okay, so here we have these particles being heated by the source, they're transferring some of their energy, and they're losing that energy and they're sinking back down only to be reheated again, right? And so this turns into a circular current. This can only happen in fluids. Of course, this is a cycle that can happen over and over again in a closed system. In other words, if these gases are sort of trapped in a big enough container, this will be a cycle that happens over and over. This is the same thing that can happen in liquids as well. And so, when we see convection in liquids, maybe you've seen like these rolling currents, these circular currents. Remember, convection only in fluids. Here's the last thing I want you to notice. Notice that in this diagram or in this animation, we have two of these convection currents that are side by side, and one is rotating clockwise and the other is rotating counterclockwise. These are rotating in opposite directions. When you see this, this is one whole thing, and we call this a convection sail. Okay, so two side by side convection currents rotating in opposite directions, those are convection sails. When we look around us, convection is happening, but sometimes it might be invisible. Of course, this happens when we heat any liquid on a stovetop, right? The fluid inside of a pan or a pot, we're going to have convection that happens there. If you've ever watched one of these lava lamps, there's a heat source down at the bottom, which is a light bulb, and you're going to have some changes in density, which is going to make things rise. Make this, it's usually wax on the inside, make it rise, and then when it cools, it'll sink again. Convection is the major driver of heat exchange in our atmosphere. So if you've heard that hot air rises and cool air sinks, then you're familiar with the idea of what's happening on a massive scale in our atmosphere. This can also happen when we trap gases in our oven, like a convection oven. These are all good examples of convection. And remember, convection is just the flow of heat through circular currents due to the changes in density from thermal expansion and contraction. So I found this example, and I wanted you to be able to see it. It's the best example I could find. Remember, I said how we can see these circular currents sometimes inside of the pasta noodles on a stovetop. So if you have ever been boiling noodles and you have seen sort of these circular currents forming, this is a really good animation or a really good short video that is showing you convection. Convection also happens deep inside of Earth's core. We're going to talk a little bit more about that later, but some of you know that Earth's core is extremely warm, and as heat flows out of it, you're going to have that heat flow that is going to be moving in these large circular currents. All right, guys, that's going to do it for today. Convection, heat flow through circular currents.